chapter 2 is a chapter on logic and reason. And we're going to be, I mean, this whole year is about a lot about logic, but this is going to be sort of your introduction to logic. It's interesting, I just took my son to University of Chicago, and the keynote speaker at the convocation was talking about how, you need to sit in your seat, how, you know, the best thing, the most important thing you can learn and get out of your education is to think inquisitively and logically, and to be able to reason through things. And so, you know, if you think of it that way, this is probably one of the most important things we're going to do, that you're going to do in your career, and that we're going to do this year. All right? We're going to start with sort of the lesser of the two logic patterns, and that is inductive reasoning. Okay? And inductive reasoning is reasoning something's, figuring out that something's true. Can you get your notes outline? Reasoning that something's true because you've seen a pattern. Our brains are hardwired to look for patterns. They are, you know, that's just, it's a constant going on in the back of your mind. You're looking for patterns, ways of making sense of the world. And so that's just what inductive reasoning is. It's looking for patterns and then guessing what's coming next based on what you've already seen. Okay? So, all right, so like Pioneer Pete says it best, I think. It says, I see a pattern and I think the pattern will continue. That's inductive reasoning. You see a pattern and you're going to go forward based on that you think this pattern is going to continue. Okay? All right, so seeing the pattern might be, it's rained every Friday this month. Okay, that's your brain is noticing that pattern. So what are you going to assume is going to happen next Friday? It's going to rain. Okay, so you're seeing a pattern, you're using that pattern to project into the future. Okay, so you're seeing that it's rained every Friday this month, so your conjecture, which is like a guess. It's not exactly a guess because it's an educated guess, I guess. It's officially a statement you believe is true because you based it on seeing these patterns. So your conjecture is like an educated guess about what's going to happen next. Okay? So your conjecture, because you've noticed that it's rained every Friday this month, your conjecture is it's going to continue to rain on Fridays. All right? So that's another vocabulary word, conjecture, that you're going to need to know. Okay? And you see this pattern. March, May, June, July, March, May, July. What would your conjecture be? We've got a September, November. And what were you basing September on? Okay, so TJ noticed the pattern March, April, May, June, July, August, and he said September. Okay, what pattern did you see? December. Okay. So his conjecture would be the next month would be September. Okay? And then counterexamples we've already studied. Okay? Remember, that's an example that makes your conjecture false. Ryan, you need to get out. Okay, sorry. All right, but not all conjectures have a counterexample because some conjectures just are true. They don't have a counterexample. Okay? So a counterexample is an example in which the conjecture, it's an example, a specific example that proves that what you guessed is not true. So if it doesn't rain this Friday, that would be a counterexample to our conjecture that it's going to rain on Fridays. Okay? what would be a counterexample to this? If 1 minus y is greater than 0, then y is between 0 and 1. If that's true, then you wouldn't be able to find any y's outside of 0 and 1, or outside of that range, that would make this true. Can anyone think of a counterexample? Counterexample is a specific example that makes the statement false. Okay? All right, and then a conjecture, again, is your guess about what's coming next. All right? And it's really hard. The hard part is you kind of have that feeling like you know what it is, but you have to be able to put that conjecture into words. And so that's the part we're really going to hit hard in this section. So okay. Yeah, will that work? Yeah, that works. Okay. All right. So tell me. But you can't use examples. So articulate the pattern without saying like 1970, 16. How would you describe it? Exactly what to do. Okay. Starting at 19 and subtract the decreasing odd numbers. All right. Does anyone come up with a different pattern? That you just go down one square root. Yeah. Well, now give me exactly what to do. You start at square root. Okay, so first thing you do is take the square root of the previous number, and then what? No. So you take the square root of this. What do you get? Then what do you do? Add 1. So you get 8. And then square it. And you get. So should the next number be 64? What should the next number be? 36. So you take the square root and get 7. And then what do you do? Yeah, exactly. Subtract 1. And then what do you do? Square root? Square it. Right. Guys, it's a hard thing to do, and I'm going to keep at you guys to be precise because it's so easy to get, just kind of know what you mean, but not. Okay? All right, take a look at this one. Okay, what do we got? Monica, any idea? Okay. Well, and that's the hard part, right? The conjecture part. Because I think you're right. There are 27. But think about what they're doing each time. So we went from here to here. What happened? Okay. Could we just draw that triangle any way we want? How did they draw it? Okay. All right. In the opposite, so the slanted side was opposite of where it was. Okay. Can anyone come up with a? Stephen?
If you take the number of purple triangles in the figure before in the previous figure, and then times it by 3.
Okay. All right. Numerically, that's one way to do it. But let's talk about what our conjecture is about how we're getting these triangles. So she's saying we're drawing a triangle. What happened to get from here to here? Okay. Why 3 more? Could we have added 4 more? Okay, so we take each triangle we created and we draw another triangle inside it. Okay. Right? Because we started with 1 triangle, so we drew 1 triangle inside. Then we made 3 triangles. So then we took those 3 and we drew a triangle inside of those. Right? Yeah. 3, 6, 9, 12, 15, 18, 21, 24, 27.
You're only putting your finger on one dot and saying it's 3 here.
No, it's 3. 1, 2, 3. 1, 2, 3. Yep. 3.
I just see little white specks. Purple, there's purple.
Yeah.
Is that how it works? 1, 2, 3, 4.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Yeah. How many purple triangles are in the figure? All right, but getting back to the specific language is we take the purple triangle. Each purple triangle, we draw a triangle inside that purple triangle, right? Like we created 3 here, and we do a triangle inside all 3 of them. Can we draw the triangle? Do we have to draw the triangle a specific way?
Yes.
What do you mean? What do we call that? How do we make sure we do a triangle in the middle?
It's not facing the other corner.
No, think about where.
It's like a right angle, and you have to put it like opposite of that right angle. You have to put it opposite of the right angle. So here's the right angle for this one. You put it opposite of that.
Well, these conjectures. Okay. The sum of 2 positive numbers is, and we're going to assume these conjectures are true, that there's no counterexamples. So the sum of 2 positive numbers is, second, positive. Can anyone think of a counterexample? 7 positive. Can anyone think of a counterexample? No, that's right. Okay, the product of 2 odd numbers is, no, it doesn't say anything about positive or negative. It's odd and even. The product of 2 odd numbers. What's product mean again? Multiply. The product of 2 odd numbers is even. Can anyone think of a counterexample? 3 times 3 is 9. In geometry, we get a lot of JKs because you think you're onto something, and then someone comes up with a counterexample. The product of 2 odd numbers is odd. All right, guys, focus. That's the way you want to do this is using inductive reasoning. Start coming up with examples. 1 times 3, 3 times 5, 5 times 7, 7 times 9. What's the pattern? 1 times 3 is 3, odd. 3 times 5 is 15, odd. 5 times 7, 35, odd. 7 times 9, 63, odd. So the product of 2 odd numbers is odd, right? That's using inductive reasoning, thinking about the pattern that's coming in. All right, now this one you might have to draw a picture. The number of non-overlapping segments formed by n collinear points, okay? It's a segment, so it's got two endpoints. All right, now start drawing collinear points in there and seeing if you can come up with how many segments you would create. Now, Lisa, we've practiced this already in class, but Prove the conjecture is false by providing a counterexample. And the first two for sure should be pretty quick. For every integer n cubed is positive. Connor, can you think of a counterexample? For every integer n cubed is positive. Negative 4, because negative 4 times negative 4 times negative 4 is negative 64. Negative 64, so that's a counterexample. Good. Okay? No two complementary angles are congruent. Michael. No two complementary angles are congruent. So we're looking for a counterexample. So two complementary angles that are congruent. Or their measures are equal, we're trying to say. Two complementary angles whose measures are equal. What's complementary mean? I'm sorry? They add up to 90. So if you think of, guys, it's really hard to concentrate when you're having computations concentrating. Yeah, 45 and 45. That's okay. And the last one, for any 3 points in a plane, there are 3 different lines that contain 2 of those points. Okay? So, yeah, draw it. So this goes back to that question you did day 1. If you got the example, this is not a counterexample, but the example would be you've got 3 points on a plane, and there are 1, 2, 3 lines that go through 2 of them at a time. I'm looking for a counterexample. When would that not be true? That there are 3 different lines that would go through them 2 at a time. Yeah, 3 collinear points. 1, 2, 3. Can I put 3 different lines through those? Nope, just 1. Right?